CascadiaJS, are you still awake? Yeah! That was not very enthusiastic. I'll take that as 50% awake. Hopefully we're going to wake you up over the next few minutes. So I hope you all enjoyed lunch. Our goal planning CascadiaJS lunch this year was to set the record for any conference for the largest banana leaves eaten off of by conference attendees, and we're not entirely sure. The Guinness Book Records people are still checking out, but shut up, Alan, and go to the speaker. So our first speaker for the afternoon is Curtis Lassam. And like me, Curtis is a software developer from Vancouver, BC. But unlike me, he also runs a webcomic and an online video series about software, which is very awesome. Curtis is a very funny guy. I invited him to speak at the Vancouver JavaScript meetup last year, and he kicked butt. So I'm excited to see what he has for us this year. Give a hand to Curtis.
Hello, everybody. I put together a calibration slide before I did this, just so that I could try to get my images sitting correctly on the slide, because it's a very visual presentation. And so I did it. I spent all of yesterday changing over my 190 slides to work with a new format. I hope it looks good. Also, this is the second or third crack at a calibration slide. Some people had other suggestions for what I could put on this many screens. And some suggestions I could have done it if it weren't for the fact that they just didn't have high enough resolution when those things were put together. So, as Alan mentioned, I'm Curtis Lassam, C. Lassam on Twitter and GitHub. I have a website, curtis.lassam.net. I work for a university in BC, but not the one you're thinking of. I work for the other one. So, SFU, that's me. I also run a webcomic online. It's at cube-drone.com. I'm sort of like Randall Munroe from XKCD, but nowhere near as intelligent or funny. And the reason I mention this is because I recorded myself giving this talk ahead of time and posted it there, so you can watch the talk while I deliver the talk, Spaceballs style. All of the slides live here at curtis.lassam.net/projects/#prez. But it's like 20 megabytes of images, so please don't saturate the CascadiaJS connection. Now for the presentation itself. Hash functions taste great with anything. So we're going to talk about hash functions. Now, I'm going to do my best to show you why this fundamental technique belongs in your toolkit. You can see from my drawing of the toolkit that I'm not a handy person. So we're going to talk about hash functions, hash tables, Bloom filters, choosing hash functions for data structures, and hashes in security. Now, you might be thinking, I already know what rainbow tables and Bloom filters are for. I'm not going to learn anything. You guys are right. So for you guys, I've hidden Portland Pete somewhere on one slide in the set. If you could tell me where he was in the presentation after I'm done, you get a prize. But before you get too excited, the prize is a high five. Maybe a business card? You get something. So let's get started. What is a hash function? Here's an example. Let's write a function that takes a string, splits it into characters, converts every character into an integer, adds the integers together, and mods the result by 100. This is a hash function. Not every hash function works this way, but like many other functions, it is a hash. It has a number of very useful properties that we can work with. Regardless of what sequence of characters you put in, you're guaranteed that the output will be between 0 and 99. The output for a string will always be the same. Many different inputs can produce the same output. And given the output, it's impossible to guess the input that produced it. I know, invoking the Wikipedia definition of something is the sort of presentation equivalent to the starting with Webster's Dictionary defines, but it's a good definition, so I'm going to use it. A hash function is any algorithm that maps data of arbitrary length to data of a fixed length. So no matter what sort of data you put in, you always get a variable within a certain range. So that's a hash function. Now let's talk about hash tables. Now, hash tables are a data structure concept used to store keys and values. Keys and values are important. You deal with them when you work with things like MongoDB or memcached or JavaScript objects. And if you're dealing with keys and values, chances are behind the scenes something clever with hash tables is happening. It could be something else like a tree or a trie, but we're not talking about those, so for the sake of this presentation, we're going to forget that they exist. So let's start with a big block of memory. Let's say an array with 100 elements. We want to store the value hash215D29 against the key color. So we run a hash function on the key, color. This produces a number, which we mod by the length of our table, which gives us an index. and then we can just store our value at the location pointed to by the index. That's a hash table, easy peasy. But it is not quite so easy, nor quite so peasy. As the array fills up with values, it gets more and more likely that we'll have a hash value point to a spot that's already full. This is called a collision. What do we do when there's already a value in the spot where we want to store a value? Well, we can keep walking forward in the table until we find an available spot. This is called linear probing. Alternatively, we could root a linked list at every space in the array. That way, our hash table can take as many values as we can throw at it. Or a tree. We could also root a tree at every space in the table. Except we can't because we've forgotten that trees exist from earlier. This, rooting a separate data structure at every spot in the table, is called a chained hash table. One problem. Here there's a bunch of different values stored where we're looking for the key cheese. How do we know which one is the right one? Well, we need to store the key with the value anytime there's a chance of collision, just so that we can make sure we're getting the right value when we're retrieving the item from the table. But even with some strategy for collision detection in place, it's possible for the table to get so full that it performs very sluggishly. A crowded chain hash table is little better than a linked list. Or in the case of hashing strategies that just shuffle addresses around, it's possible for the table to become completely full. When this happens, it's time to rebuild the hash. This is a time-consuming process of addressing an even bigger whack of memory. Taking all the keys out of the first array, rehashing them, and then putting them in the second array. There's one language I can think of whose default hash table implementation can perform this computationally intensive rebuild step unexpectedly anytime an insert pushes the table above a predefined load limit. But for the sake of politeness, I'm not going to mention which language. Of course, linear probing and chained hashing are not the only hash table management strategies. There are many, many ways to manage a hash table, like Robinhood hashing, which steals data from your richer tables and inserts them into your poorer tables, or hopscotch hashing, where you implement the entire array in chalk on the pavement. Definitely right about those last two. No need to check them on the internet. So a hash table is a data structure that uses the result of a hash function as the location to store the data in memory. Insert, constant time. Delete, constant time. Lookup, constant time. Search, don't search through a hash table. It's a bad idea. So that first few minutes of the presentation was there to get you up to speed on the basics. Now let's have a talk on some of the meat, bloom filters. So a bloom filter is a great way to keep balloons out of your face. How did this slide get in here? Oh, that's not right. Okay, a bloom filter is a data structure that's fast and space efficient, used to test for membership in a set. That's important. It tests for set membership. It doesn't store any data. It can tell you if something is in a set, but you can't retrieve an item from the set. Like if we have three objects, banana, apple, and bowling ball, and a bloom filter representing the set of fruit, we can use the set to determine that banana and apple are fruit and bowling ball is not, but we can't give you a list of all the fruit that were used to populate the set. We don't know them. So a lot of the time, bloom filters are used to answer questions like, is chumpies a real word? No, it's not. Is evil.ru a malicious website? I don't know, maybe. Is main.css in the cache? Yes. Yes, it is. And is this a banned image? So let's look at this image problem a little bit. Let's imagine we're running a forum and our itinerant users keep posting the same images again and again. There's gigabytes of this one image just sitting in our storage. We want to detect when the user is sending us a repeat image and instead replace it with an image link that already exists. Let's say we run a hash function on the target image. Yes, you can hash images. You can hash most anything. And mod the result by the length of an array. Move to that index location in the array, and save a link to the image there. Then, when we're checking a new image, we can hash it and see if it's in the array. Of course, this is just a bog standard hash table. I'm supposed to be talking about bloom filters. This works fine, but it takes a lot of space, and I promised you space efficiency. Let's imagine there are 5,000 images we want to keep out of our forums, and they take up 100 kilobytes each. Using the same math that you use when you're buying hard drives, which is not correct math, it's about a 500 megabyte table of images. So, while it's not a ton of space, you probably don't want to keep 500 megabytes sitting in RAM or send a 500 megabyte bloom filter to your user in JavaScript. Remember, though, we don't need storage from our data structure. We're only interested in whether or not the image exists. So let's imagine that instead of storing images in the table, we just store zeros and ones where our hash functions land. That way, we can check if an image is banned by hashing it, modding it, and checking if that spot in the array has a 1 in it. If there's no 1 there, we can't possibly have seen that image before. There's only one slight problem with this technique. What happens when we have a different image that accidentally collides with an image that we placed earlier? Well, this creates a false positive and unfairly takes pictures of Nicolas Cage out of production. So how do we stop collisions like this from occurring? Well, we can use a hash function that guarantees an astronomically low probability of collision, like MD5, for example. But with the astronomically low probability of collision, you get axiomatically an astronomically high number of potential outputs. With 1 bit for every potential output, you're suddenly saddled with 4 times 10 to the power of 25 terabytes in your bit array, which once again is just a little too big to put in your RAM. It does hit on one of the 2 strategies we can use to reduce collisions in this array, though. More space. Now let's take a look at the less obvious strategy for reducing collisions. More hash functions. Instead of hashing our image just once, let's hash it twice with 2 different hash functions. This gives us 2 different locations in the table, and we can store a 1 at both of them. Another image might share the result of one of the hash functions, but it's not as likely to share the result of all of the hash functions. And if any of the hash functions point to a 0, we know that this object can never have been entered into the Bloom filter. So this is a Bloom filter, a bit field and multiple hash functions to set the bits in that field. We put items in by hashing them multiple times and setting 1s at the locations that we get from the hashes. And we check by hashing an item multiple times and checking if there are 1s at all of the locations. It's actually very simple. So the thing is there are some downsides to this strategy. Because each item we put in the Bloom filter has multiple hash locations, and there can be some overlap, we can never delete anything from the Bloom filter. If we do, we run the risk of accidentally deleting something else from the filter that shared one of the hash locations that we set a 1 at. On top of that, we've reduced the chance of collisions, but it's impractical to reduce that chance to effectively 0. So there's always some chance of a false positive. However, this probability is something that we have control over. If we know the acceptable probability of a collision, let's say 0.1%, and the number of things we want to put in the filter, as we mentioned before, 5,000 images of ponies, we can use the hand-wavy math that I show you here to determine how much space we need and how many hash functions we need to get an optimal solution. Now, you don't necessarily need to actually implement this math, although it's not too difficult. You could just go to a library for this. So what we need is an array of 71,888 bits, which is 8.8 kilobytes, which is small enough that we could comfortably keep it in RAM or even just send it to the user. It's certainly easier to work with than the 500 megabytes of image that we were dealing with before. It also takes 10 different hash functions. A lot of the time, Bloom filters are paired up with other data structures that handle the storage of the items. For example, they're very useful when paired with data structures that exhibit worst-case performance when you're searching for items that just aren't in the data structure. For example, a linked list or an unsorted large array. You always get the worst performance when you're looking for something that just isn't there. The Bloom filter can check before you hit that data structure whether or not the thing is in the data structure. They're also very useful when the retrieval step for data takes a long time. For example, when a network call needs to be made to a faraway database, a local Bloom filter is a wonderfully fast way to know if you're wasting everybody's time looking for something that doesn't exist yet. Or data with a very low hit rate. If you're dealing with the sort of data where you're getting 10 misses for every hit, you can catch all of these misses with a Bloom filter. Google Chrome does this. When checking if a URL is malicious, it maintains a small, fast, local Bloom filter seeded with malicious URLs. If the Bloom filter flags a URL as a possible match, only then will Chrome make the milliseconds-long round trip to their servers to check the details. This use case matches up pretty well with our list of times when a Bloom filter is useful. A call to a remote server takes a huge amount of time compared to running a few hash functions. And maybe only 1 in 100 websites you ever visit will actually trigger the Bloom filter. So in summary, Bloom filters are a fast, compressed, storage-free data structure used to check for set membership. It's implemented as a set of hash functions pointing to locations in a bit array. It doesn't allow for retrieval, and it doesn't allow for removal. Now let's talk about how to pick which hash functions to use when you're building a data structure. I mean, I showed you my awesome cheese hash function earlier, but it's terrible, and on top of that, it really only works on strings. Now, the number of different hash functions are countless, each one a unique snowflake. Only 3 of these are made up. If you're wondering, Pearson hash is real, Lester B. Pearson hash is a prime minister, Sum32 is real, Sum41 is a band, and city hash is real, but country hash may destroy your rabbits. So, which hashes do we pick for our data structures? Well, for data structures, the 2 properties we're looking for are that they be fast and that they be well distributed. When we say fast, what we mean is non-cryptographic. Cryptographic hashes are awesome. They have a bunch of properties that make them totally badass for security functionality. The most important one being that they're collision resistant. It's astronomically unlikely that you'll find 2 different items that hash to the same value. But these cryptographic features are also really processor hungry. So we should avoid hashes like SHA or MD5 when we're working on data structure stuff because we don't need awesome security features in our Bloom filter. It's just a waste of CPU cycles. So non-cryptographic and well distributed, which means that no matter how similar your data is going into the hash function, the output should appear all over the spectrum. Hash functions that exhibit this quality are called avalanching hashes because small changes in the output lead to large changes in the output. I think I said output twice there. Terrible. Okay. Of course, this is also a desirable property in cryptographic hashes, but this one we're willing to blow precious processor cycles on because it is crucial for use in data structures. A common hash function used for this purpose is the non-cryptographic, well-avalanching public domain murmur3, implementations of which exist for most modern languages and which has appeared in numerous open source products, including Hadoop, Cassandra, and Nginx. It also takes a seed value, so you can create dozens of different hash functions out of murmur3, just by changing the seed value. There are about 5 different implementations of it on NPM. One other thing, we hashed an image to put in our data structure earlier. What sort of hash function works on an image? Well, most of them really, but a perceptual hash, or p-hash, is designed specifically to cluster very similar images together in the hash output. For example, if it's the same image, but sized larger or skewed to the left, it should end up with a hash location very close to or identical to the hash location of the original image. Of course, by nature, this hash function won't be distributed in a way that will be useful for an optimal general purpose data structure. It's the opposite of an avalanching hash. Small changes in the input lead to almost no changes in the output. But we can abuse that property so that false positives are unfairly clustered on images that look very similar to our band images, which would actually probably be a good thing for our use case. So you can try it out with an npm install phash. Okay, so that concludes the data structures portion of the presentation. Let's talk about how hash functions contribute to the security of your application. So you're running a web application and the worst case scenario happens. Some hacker makes off with the user table from your database. How? I don't know. For the sake of argument, let's say SQL injection. At this point, your users are all shit out of luck, right? I mean, some brigand has made off with all of their passwords. Most of you who are a little bit, just anybody who's worked on the back end knows that no. Our developers have cleverly obscured the passwords before saving them. So in order to hide passwords this way, when the user creates an account, we don't save the password. Instead, we save the result of a hash function. Later, when the user tries to log in, they provide a password. We hash the password and compare it with our hashed password for that user. If the two match, the user has provided the correct password. Of course, if 2 different passwords ever collide, if 2 strings hash to the same output value, then it would be possible for someone to log into our site with the wrong password. And that's bad. Do you remember earlier when I said that cryptographic hashes like MD5 have a feature called collision resistance, which means that 2 inputs are astronomically unlikely to collide? Here is where that is super important. So now our passwords are protected. Yep, totally protected. Nothing could possibly go wrong. Dictionary attacks, the way to break hashed passwords. So we've stolen a whole database full of usernames and hash passwords, and we want to get at the raw passwords so that we can try them out on banking sites and such. What we can do is try to create a list of everything that we think of as a possible password, an enormous, comprehensive list that we cull from dictionaries and years and numbers and dates. Then we use the same hash that the programmer used to hash the original passwords, And we run that on every single password in our gigantic password list. Now we have a giant collection of hash-to-password pairs, which we can compare against the original data. Anytime we find a match with one of the hashes in our set, we know what the password must have been. This checking of every hash in the set is n squared, but inherently very parallelizable. So with a bit of optimization, this can run very, very quickly. This is called a pre-computed dictionary attack. It's important to note that this isn't a rainbow table. A rainbow table is a different thing involving hash chains that accomplishes the same task but using much less storage space. I'd go on at length about rainbow tables, but I've timed this talk, and if I go on for too long about rainbows, I don't finish in time. So the MD5 hash function is so common that Juuso Salonen, and I hope I pronounced his name right, but I can't be sure, released a utility called BozoCrack that works by taking a hashed password, searching for it on Google, and then just MD5 hashing anything that comes up in the search results. It's not as effective as a proper MD5 dictionary attack, but it's still really depressingly effective because people keep using just MD5 to hash their passwords. So part of the reason that these attacks are so effective is that because every user's password has been hashed with the same hash function, it's possible for us to test passwords against the entire table. While it's unlikely that we'll ever crack all of the passwords, we're able to suss out the users who have simple passwords very quickly. Just testing the whole database against the 1,000 most popular passwords should only take you like half an hour, and just doing that will get you hundreds of people who just used password 01 as their password. So what we want to do is reduce the effectiveness of this kind of attack by using a different hash function for every single person in the database. This doesn't actually mean we need to enlist thousands of different hash implementations. What that actually means is that we want to seed our hash function with a different value for each user in the table before we hash the password for that user. It has to be a value that we have access to because we need to be able to recreate this custom hash function every time we check the user's password. And it's quite common to use the username for this password. That doesn't mean you should. Cryptographers recommend that you create a large block of randomized data and save it against the user to use as a seed instead of just the username. So this hash seeding value is called a salt. So a salt is random data used as additional input to a hash function to protect against rainbow table attacks, dictionary attacks, and really any brute forcing of the password. So that covers the very basics. And when I say basics, I mean very most basics. This isn't exactly state of the art. Unix's crypt function first used salted hashes to protect against dictionary attacks in 1976, a full decade before I was born. So let's talk about the next step here. Actually, I'm going to go back to show you all the steps. Basics. Don't use MD5. Don't do client-side crypto. And HMAC and cheese. So don't use MD5. Let's talk about that. I've been using MD5 as my de facto cryptographic hash example for this presentation because it's well known and well understood, and it's been the sort of the standard for a long time. Unfortunately, in that long time, cracks have begun to show in this venerable hashing algorithm. The biggest reason to avoid MD5 is simply that it is too fast. It's possible to MD5 hash millions of values per second. This makes brute force attacks against MD5 passwords very, very easy. This MD5 hashing Python script I wrote runs on a cheap little virtual machine, 1 million MD5 hashes in 1.5 seconds. You'll notice it's in Python, so those of you in the first 3 rows can take this opportunity to throw wadded up paper at my head. No? Okay. Now, bcrypt is designed to be slow. Using the default settings on the same virtual machine, this run would take 3.4 days. This, combined with a salt for each individual user, means that brute forcing passwords out of a database could take days or months per user, instead of an hour or 2 for the whole thing. Bcrypt also comes with a work variable that you can crank up to make things even slower as hardware gets faster. When I turn it up to 15, my million hash script goes from 3.4 days to run to 26 days to run. At this point, though, just logging a single user into my website could take as much as a second. I'm not sure if they're willing to wait that long. One of the key rules of security is don't roll your own. Don't try to be clever and implement a solution that seems like it should work. Do a little bit of research on the problem space and use something that's designed with your problem in mind. Or get a specialist if you can. Not me. I don't know a damn thing about security. But for password security, you should use something that's specifically designed for password security, like bcrypt or PBKDF2. Or scrypt, which isn't on the slide, but I want to mention it anyways. Even for general purposes, if you're looking for a secure hash algorithm, MD5 is kind of old and broken. SHA means secure hash algorithm, and SHA-512 has become a new standard for hashing, one that's cryptographically much more secure. So that's don't use MD5. Now let's look at don't do client-side crypto. So listening to this, you might be thinking, why send the password to the server side at all? The user could just hash their own password and send the hash password to the server for verification. We could go totally stateless. We could start including a hashed verification code with every instruction we send to the server. That way nobody can tamper with our instructions to the server. It sounds perfect. Well, there are two different possibilities here. Either we're trying this from a browser, or we're not trying this from a browser. Let's look at the problems of trying this from a browser. What are we trying to accomplish here? We don't want people to be able to see a password when they inspect our traffic. We don't want people who can inspect our traffic to be able to act on behalf of our users. So we send our users a bit of code that will allow them to obscure their credentials when they communicate with us. Except if people can inspect our traffic, they can also alter our traffic, which means that they can replace our crypto code with equivalent code that steals credentials. JavaScript browser crypto is exactly secure as the transport layer providing it. So JavaScript browser crypto over HTTP can't possibly be more secure than just using HTTP. And JavaScript browser crypto over HTTPS is secure as just using TLS, which is sort of secure. So I trust that you can solve for the value of JS browser crypto in this equation that I put on the screen. Let's imagine then that we're not doing this from the browser, but instead from a trusted library that we have total control over. And we still want to keep bad people away from our user data and out of our application. Well, if we just send a token containing a hash of our password, all the bad people have to do is steal that token. They could start running dictionary attacks on it. Plus, with our token, they can still pretend to be a user pretty effectively. That's bad. So what we need to do is hash the password and a timestamp together. Then the server, no, that won't work. Couldn't the attacker just steal our timestamp message and replace the command with their own malicious command? This gets really complicated really fast. We shouldn't be in the business of designing our own security algorithms. The hash function is a building block, but we need more guidance when it comes to problems like this. Which brings me to my final section in this topic on security, HMAC. HMAC stands for Hash-Based Message Authentication Code, and it's sort of what we're trying to produce here. If the problem that we're trying to solve is that we need to sign a message that we're sending to the server and have the server trust that we're the ones that sent it, the HMAC standard defines a way to perform this step safely. But it doesn't solve all of our problems. People can still snoop on our traffic. With no timestamp, people can still replay our messages to the server with impunity. HMAC solves some problems, and it's a useful tool, but if we want privacy and for our system to reduce tampering from outside sources, it's just not enough to have HMAC. So what we want here is encryption. So what we need is a full-blown encryption algorithm like RSA or a full-blown protocol like GPG, or if we're already married to the HTTP stack, TLS. The take-home message here, though, is you really, really shouldn't try to build your own encryption algorithm out of hash functions. It's like trying to build a car by yourself. You can probably do it, but the result probably won't be that safe unless you did a lot of research first. So that was hash functions, hash tables, Bloom filters, choosing hash functions for data structures, and hashes in security, which means I'm done. Thanks for listening.